okay, and ensure unique, and we copy it from the old dark. Okay. And so, sorry, let's write up here. This is 18 picoseconds, isn't it? So we can just run it. Then we go for 60 picoseconds, okay? And we call it 60 picoseconds. And we run it. Then we take 600 picoseconds. Right up there, 600 picoseconds. And we run it. Then we take 3 nanoseconds, isn't it?
Yep.
And we write up here 3 nanoseconds, okay? And we run it. It's so that you know what the hell it is each time. And then we do 10 nanoseconds? Yeah, isn't it?
Yep,
10 nanoseconds.
We change.
And we change up here 10 nanoseconds. The most important thing is this: input data is intensities without anomalous data. Okay? That you need to keep like this, because it takes different kinds of input, and that's the one we want. Okay, so now we have everything. The next thing is we go and open Phoenix. Okay, and so you've done all dark, isn't it? And you've done,
But
so you're,
I think this one is not quite.
what happened with this one?
I just tried to put the sidechain there.
Oh, okay. So it's probably not very good.
Yeah,
So
not very
let's take
good.
this one for the
Yeah.
moment, isn't it? So
Yep.
we take number 8. Okay. And so we go to difference maps. Okay. And now we click on maps here in crystals, maps. Okay. And then in maps, we generate isomorphous difference map. Okay. And we're going to do 18 picoseconds minus dark rough. Rough means that we haven't scaled it. So let's write in non-scaled. Okay? And so our first file is always the one at the beginning. So it's 1 minus 2.
Or 1 minus 2.
Okay? So that means that we now take 1 should be 18 picoseconds,
18 picoseconds.
the truncated one.
Yeah.
And
The
2 should be where is it?
Oh, you mean
all dark.
all dark.
Here, isn't it?
8.
No. All dark
Oh,
truncate.
truncate, yeah.
So that's what we want. Okay. Now the PDB for phasing is 8.
Well,
Okay.
I think that is the new one. The new one.
Sorry,
This one.
but this one you have modified. So no.
Oh, yeah.
The one that came out.
Yeah, that's
So,
correct.
so and now you set it to structure factors, not to intensities. The comparison. Okay. Now the high resolution is the worst high resolution of the two. You have it up there, isn't it?
Yeah,
So show me the table, and then we can take a look.
not this one. 18.
Yeah, 18 picoseconds.
1.
1.53. So we write here 1.53 to 10. Okay.
Okay.
So why only to 10? We have more data. Well, the reason is that in general, the closer you are to the center, the higher the intensities. Okay? And so that means that in a way, what happens is that the low resolution data can completely dominate everything else. Okay. And then you see nothing about the side chains or anything like that. So that's why you cut it off to keep it relatively low. However, for extrapolation, you look at everything. Okay? So, and then because you want a very nice and clean map, you set here your sigma to 3.0. So that means that you're only going to use structure factors that have an I over sigma of 3 or higher. Okay? So why 3 or higher? Quite simple. If you think about it, if you take 3 and do the square root of 3, okay, you get to about 2.
2, yeah.
So in that way, you are close to the standard setup. Okay? And then finally, you go to advanced options, and you go to you click on multi-scaling method. So what this will do is it will try to scale it to each other. It won't be super good, but it's better than nothing. Okay, and so we run it. And then we can run the next one. which will be what, 60 picoseconds, isn't it?
Mm-hmm.
Go here and write 60 picoseconds, and we take the 60 picoseconds, this guy here. Okay. And what's the resolution of 60 picoseconds?
Here.
1.55.
Yeah.
1.55. So we run that one, okay? And run. Then we do 600 picoseconds.
600.
And what's the resolution of 600?
1.53.
So we take this one
Yeah.
and 1.53. Okay. And then we take 3 nanoseconds, isn't it?
Yeah. 3 nanoseconds.
And we take 3 nanoseconds. What's the resolution?
3 nanoseconds. 1.54.
4. And then we take the 10 nanoseconds. What's the resolution?
1.50.
1.5. Okay. So simply 1.5. And then 10 nanoseconds. And we run it. Okay, and now we have the data. So let's take a look. Wow, that looks pretty. That's a lot of changes already. So you can see at 18 picoseconds, we can see movement of the arginine and movement of the aspartate. We can already see very clearly
Oh, this is
the movement of the asparagine. We can already see very clearly this movement around here, isn't it? And let's see, we can set it a bit higher, okay? So to clean up a bit. And so we can see here, so this is the, you can see this is the first tryptophan.
Where? This one?
This one here.
Oh, this one.
This one is the first tryptophan. See?
3
It
nano.
goes, jumps from here to here, okay? And from here to here.
Second one.
And you can see that around the second tryptophan there is already signal.
Oh.
You see? We don't see much of a change in the tryptophan itself, but we can see that these,
Oh.
they have moved. So that means that probably we have already a significant change going on around that tryptophan.
Oh.
Okay, so that the environment around the tryptophan has been modified here. If you remember, this should bring us to the 18 picoseconds, if I remember, is somewhere between these two.
I mean, the first and the second tryptophan.
Yeah.
And the first tryptophan to FAD, I think, is within 1 picosecond.
Yes, exactly.
Mm-hmm.
So that's why we can see that already here, okay? Then we can take a look at the next one. So this is 60 picoseconds. And so we can go to 3.5 to clean it up a bit. And we can see the movement on the asparagine already very nicely. We can see the movement down here of the arginine and aspartate. That also looks extremely good. Now we can go to the first, where is that? So here, let's move it like this. Okay, and sorry, let me turn it around. Here. So here's the first tryptophan. Here's the second one. And here's the third one. And so now you can see that the signal has moved
Yeah,
to the third one.
Yeah.
Okay, so that looks really nice.
Mm-hmm.
So now we can take a look at the 600 picoseconds. The 180 is the really interesting one, because that's where it's really on top of the third tryptophan, if I remember correctly. So okay, so we have lost movement here, you see. Okay, then let's see. So this is what, 600 picoseconds?
Yeah.
Or? This is 600 picoseconds. Okay, so that means that by this point we expect things to happen up here.
Already down to,
Yeah, so we should be expecting
tryptophan,
something around here should be starting. Okay, and so we see some effects already here, but not much, isn't it? And so finally, so we can go to 3 nanoseconds. And what do we see here? So we start to see more movement again here. Actually, we can take a look at the other one a bit later, because it may need a bit lower sigma. But we can see the movement here. We can see that there is not so much movement down there. That's pretty interesting. We see here the movement of the asparagine. Okay, and so if we go to 3 sigma, we can see it a bit more clearly, and you can see that now it's like this.
Oh yeah.
See? So now we can go to 3 to 1, and there you have it. The movement of 3 to 1 is very clear to see.
Yeah.
And that water has moved as well. Okay, so that looks very nice. Okay, now I would like to see back this guy here, the 600 picoseconds at 3 sigma, so to see a bit more closely what's happening. So we can see the movement here. It's just that it's a bit weaker than the other ones. We still can see movement on the aspartate, not so strong. On the glutamate, and we can start to see signal here.
Oh.
See? So we were looking at it like this. If we look at it like this, clearly we're starting to see the same signals that we see at 3 nanoseconds are starting to appear already here. Remember that we expect the movement to take place in about 800 picoseconds. So this is sort of a bit early for it, but we should see some changes going on. And then 10 nanoseconds is the last one. And let's set it to 3.5. So this have moved out. See? Yeah. So then we already have the rotation there, isn't it? We already have signals. So this signal is still here, but not too much. We can go to 3 to 1, and there you have it. That signal is very strong and nice. See? See ya. So yeah, there you have it. Looks, I would say, very nice overall. Okay. Now you need to take a look at the other ones. Okay. And soon you can start to look at the. Well, I'll show you how to. Sorry.
Keep refining the dark one.
Well, I mean, you need to continue refining the dark
Yeah.
one. That's for sure. But no, I mean that's at this point, slowly you can start to see if you can start to extrapolate and so on. I think the dark one should be almost there. Let me see if I can see what the no, this, sorry. We can go to all dark, isn't it? And this one. Oh, I would just like to see what's going on with it. So what's the region where you had issues? So okay, this guy here, for example, needs a lower occupancy for sure. I don't know what this is, but this is bullshit. There's a lysine that has been exploded. You see? You just don't have that information, and it's exploded into. So these are the protons, actually, if I can see it correctly. Yeah, these are protons. Those you need to delete as well.
Oh.
Because they have exploded like that. Okay? And that's basically it. So where's the region where you had trouble?
I think 50 something.
Sorry, what?
50.
50?
Yeah.
50?
Yeah.
So we can go there. Okay, and we set it to what? 1 sigma at first. Okay. And
I think here, around here.
yeah, that's right. Over here. So you need to model the entire thing basically to be able to build it. Okay.
You mean delete all of them then?
No. Well, I mean, delete the water, but then you need to generate alternative amino acids going through all of this to build it. Okay.
And try to use the residue that the same and move
Sure.
them around.
Yeah. So, but you need to generate. You haven't generated the
Yeah.
alternative residues. So you need to generate the entire loop as alternative residues and then build them through up here. Because clearly you have the connection up there. Okay.
Yeah. Okay.
So if you need help, let me know. But but yeah, this needs, what's the measurement here? Set it to 0.5. Okay. And then the next one, sorry, not this. Where is it? Difference map peaks. Hey, oh, and you have, that's something that you need to build still, that lysine.
But when I build it, it just.
Yeah, you have to add two or three atoms in there and delete the rest. And that water is not in the right place.
Okay.
Okay, so you need to look into the difference map peaks and check where things are going. See, this one here, the problem is you actually have it. You see? It's there. But I don't know why. Delete hydrogens and residue. Let's just kill them. And then they're gone. Okay, but you have here, and you actually have a double conformation. One here, one here. You see?
But I think this signal just.
And here you have the same problem. This is these are the valine hydrogens.
Oh.
Okay. So off they go. Okay. Then here, these are these guys. I don't know why they're exploding all over the place. And delete hydrogens and residue. Done. See, now they're gone.
Oh. Okay.
Okay. So yeah, you do have quite a bit to work on here. Okay. Wow, what happened there? That is not there. That is definitely not there.
Yeah, I know.
Okay. Or I mean, maybe there, but just at a very low occupancy. You can try and lower. So basically, what you can do is set the occupancy to 0.5.
And to see what happened.
Yeah, because it's gonna try and do an occupancy refinement. And then it's just gonna run an occupancy refinement and see how much it
Okay.
set it up. Okay. So yeah, that's that.